it is my pleasure to introduce Harald and Dieter, who are here to talk about GSM hacking, specifically running your own GSM network. So if you'll join me in giving them a round of applause, please.
Well, thanks for the introduction, and thanks for everyone to be here. It's definitely an interesting topic, and I was wishing to present on something like this for quite some time. Unfortunately, we didn't actually manage to get it done until now. So this talk is about how to run your own GSM network. And obviously the first question, well, not to many hackers, but to many other people, the first question is why? Right. So, why would you want to do that? Well, obviously for the same reason you want to run other networks. I still remember when I was like, I don't know, 12, and I bought my second PC, and I put the first Ethernet between those two systems. And sure, you can learn and experiment with technology. You can understand how it works. Especially when we talk about the open source community, then to some extent, in this case, to boldly go where no man has gone before. For me, really, the underlying reason is that there are so many different security problems with GSM that people inside, well, let's say the IT security community are aware of. And which are theoretically documented or theoretically known, but nobody really can demonstrate these problems because, well, nobody who wants to demonstrate the problems operates a network. So this is a very important fact. I mean, for example, the number one problem with GSM is that the network authenticates the mobile device, but the mobile device does not authenticate the network. So anyone who comes up with a network and says, well, I am whatever kind of network, people will log into that network. And there's no way how they can determine whether they are on the legitimate network or on an illegitimate network. And this results in all kinds of other problems. And something like this has to be brought to the public attention. There are like literally billions of GSM users out there who have no clue about the insecurity. You know, they use this for payment systems that facilitate GSM. You know, for online banking where SMS is transported over GSM in some cases. For all kinds of applications where people typically assume confidentiality or privacy or whatever kind of other security features, which I believe nobody has ever indicated that they actually exist, or nobody ever stated that they were there. Anyway, so raise public awareness about the problems that are here. So a legal disclaimer, don't try this at home. GSM operates in the licensed spectrum, at least in, well, almost all parts of the world that I know of. So in order to operate your own GSM network, you need approval from the respective regulatory authority. So you, in fact, can only use the BTS with a dummy load, basically not transmitting any signal. And obviously, don't interfere with any operators. This will be a very unpleasant experience, I can assure you. I'm just having a very vivid imagination. So, the software that we are talking about is, and this is really true, it is for research, right? I mean, we want to point out and demonstrate the problems that GSM has. And that's the reason the software is being developed. The software that we're talking about is mainly 2 programs, and those 2 programs will be released as open source later today. And there will be an according wiki and so on. So, we need to talk a little bit about GSM, because unfortunately, at least it's my experience, not many people know too much about the details, or, well, at least whatever, I mean, there's all kinds of details, but even the very, very high-level details, many people don't really know about GSM networks, which is, again, one of the reasons why we need this kind of technology in the hands of the people. If you look at the amount of security research that is being done on TCP/IP and the internet and so on, and you look at the amount of security research that's happening in mobile phone networks, then it's probably, I don't know, 1,000 to 1 ratio, if not more, maybe 10,000 to 1. And that's weird, you know, it shouldn't be like that. And so more people need to learn about GSM, and that's obviously easy with open source software and so on and so on. So unfortunately, there is no hitchhiker's guide to GSM networks, and the literature that you can buy in form of books is typically either extremely low-level RF, which normally most people don't care, especially not people who deal with security, or it is extremely high level, more to the extent of how do I design a network, how do I deploy a network, how do I position the cells, and this kind of stuff, which is obviously not interesting as well. So then you have the protocol specifications, which are publicly available, which some people are surprised by that, but yes, you can get everything but the encryption documentation. And it's 1,108 PDF files, 414 megabytes. I don't know how many pages. I wanted to implement a script that counts the pages in all the PDFs, but I didn't find time for doing that. But what I did is actually convert them all to text so I can grab them. Anyway, so the specs are out there, but it's really hard to get started. And this has been a process, at least for myself. I don't know how it is for Dieter, but I have been learning more and more about GSM throughout the last, I would say, 3 years or something like that. Not full time, right? It was just here and there, learning bits and pieces here and there, and after some time it starts to make sense. So if you look at the GSM network architecture, then it's like if you don't know about telecommunications networks, then it's very, very different than like if you just have a TCP/IP internet kind of background or Ethernet kind of background. It's a bit synchronous network, sort of fits into the entire telco industry's synchronous digital hierarchy, SDH. Has many analogies from ISDN. Oh, this is supposed to be SDH at the end, by the way, not SDN. The layer 2 is modeled after Q921, which is the layer 2 of ISDN. It has some extensions. The layer 3 call signaling, only the call signaling, which is only one particular small part of the entire GSM system, is modeled after Q931, which is the basis for example, the Euro ISDN protocol, which is spoken on ISDN systems all over Europe, at least. So there's all kinds of other protocols for management of radio resources and so on and so on. However, there's one thing that is, again, very similar to the traditional telecommunications network in a sense that the logic or the intelligence is built into the network, not so much in end-to-end. So if you come from an internet point of view, then you have, all the entire protocol stack on both ends of the connection, and the network in the middle is very stupid. It just passes on packets. That's extremely different in GSM. I would call GDSM a TDMA nightmare. I've been working a bit on other projects as well for GSM protocol analysis, so just passive sniffing of GSM. And it's very, very hard to understand who sent some data or for whom data is sent at a given point in time without knowing tons of contexts and keeping very accurate timing and so on and so on. It's not just that there are like 8 time slots on a radio channel. That's very easy, no, but it's the multi-frames, hyperframes, and all the complex setups on top. Anyway, let's go on. So what do we have in a GSM network? We have a mobile station. We have a base transceiver station. It's important to say the base transceiver station because it really is a transceiver. It's not a base station. But if you say it's a base station and you think of something that actually can interact by itself with the mobile device, that's not the case. It's just a transceiver. You have a base station controller, which implements all the logic, a mobile switching center, and so on. I'm going to talk a little bit about what these individual parts do. So the BTS is the base transceiver station. It handles the layer 1 of the radio and parts of the layer 2 on the radio side. It handles obviously the modulation, demodulation. There's an RF power amplifier. There's VCOs and so on and so on. The time multiplex, the scheduling of frames, these kind of things are done by the base transceiver station. But as I said, it's not a self-contained base station. It doesn't do anything by itself. The base station controller has to tell it everything. Like, base station controller has to indicate what kind of beacons to send. Base station controller has to decide at which power level to send which frame, and so on and so on. So it's a fairly stupid, in quotes, device that just has some kind of offload capability for the base station controller. The base station controller then does the actual decision making for most parts of the protocol. It controls almost all aspects of the base transceiver stations. And also handles handover between different base stations in one base station controller. So you have one base transceiver, you have a number of base transceiver stations which are all connected to one base station controller. And if you roam between those base stations, or if you hand over between them, then the base station controller takes care. If you move to a base station that connects to a different base station controller, then the base station, the mobile switching center gets involved, which is the next element in the hierarchy. It handles switching of the actual calls. It does what's called, that's literally a term from the standards, interworking with ISDN, or the analog telephony systems, talks SS7. And then you have the home location and visitor location register, which has the database for the subscribers and so on and so on. So the interface between the base transceiver station and the base station controller, that is what we have been working on mostly. It's called ABIS. I have no idea what ABIS is supposed to mean. It's based, like the physical layer is an E1 line, S2M sometimes called in Germany at least, so 2 megabit synchronous link that exists in SDH. And it has a couple of protocols on top of that. It's layer 2 management, which is for TEI establishment. If somebody has dealt with ISDN before, you know TEIs. The organization maintenance layer and the radio subsystem layer. And basically you have one time slot on the E1 which has the actual control channel, and the other time slots then have speech data. I'm going to go a little bit more into detail. So the ISDN E1 interface basically has 32 time slots. One of them is CRC, so 31 are remaining, and on one of these 31 you talk the actual signaling, and 30 time slots remain for voice data. There's a particular encoding on the wire, but these are all details that we do not need to get into. And despite this diagram says that time slot 16 is usually carried for signaling, this is in ISDN. In the ABIS protocol on GSM, you can actually configure which time slot the signaling is running on. We are doing it on time slot 1, for example. So, now for the speech and data traffic, I'm going to hand over to Dieter.
Okay, I will tell you something about how speech is encoded. We have basically, we have basically two different signaling streams. There is the signaling to the base station transceiver, which controls the ear interface, which goes to the mobile equipment. Then there is also some sort of operation and maintenance stream, which controls the base station itself. It tells it what frequency it shall use and such things. Those streams are controlling streams. They are only they are handled in packages, and a message is sent and tells the station do this or that, and it gets back a result. Speech is different on data traffic. It's transmitted all the time. If there is no speech, you receive some sort of idle frames. There is nothing inside. It just tells no speech going on. Speech traffic is handled in one of the time slots we have in the ISDN channels, and you can configure the time slot which is used for transferring speech or traffic. Speech is The speech and data traffic is usually divided in the time slot in 4 different subslots. Basically, you don't need the full weight of 64 kilobits, so you divide it in 4 subslots with 16 kilobits each. This division is very simple. You take the first 2 bits for the first subslot, the next 2 bits for the second, and so on. This stream is then the stream does not have any synchronization marks. You just have this data stream and you have search for the synchronization by yourself. You don't see speech is starting, speech is ending. You have this data stream and you look for it in the packages for where the package starts and where the package ends. And then you have this package with, in GSM is encoded, which holds 20 milliseconds of speech. This 20 milliseconds of speech is repeated with 50 hertz frequency, so you get a continuous stream of single packages of compressed speech. In GSM, speech is compressed using several codecs. The most common ones are full rate and half rate. Full rate is 16 kilobits, and half rate is, as it says, the half one, 8 kilobits. And we have also several newer and better codecs. For example, there is the enhanced speech codec, but in our case, we only talk about the full rate codec because this is what we have implemented so far and which is also supported by our base station. For the full rate codec, you find open source decoder, and you can use it to decode and encode GSM full rate speech packages. You just take an audio file, put it in, let it run through the encoder and get the compressed files. But these compressed speech packages are not the packages which are transferred on the ISDN layer. Basically because those packages don't contain the synchronization framing. If you send them, you can't find out where a package starts and where it ends. So they are put in so-called TRAU frames. TRAU is actually the unit, the transcoder and rate adaptation unit, which sits in the GSM network and which takes care of transferring speech into, for example, ISDN speech, which is then transferred to the local, to the Earth-based network. And those TRAU packages contain a header which allows to synchronize them. This header is a specific bit pattern which is only used in the header, and so it can be easily detected. Basically, this fills this adds some overhead, but the overhead is not too large. We start with 30 kilobit, which we get 13 kilobits per second, which we get from the GSM decoder, and we end with 16 kilobit after putting them in those TRAU frames.
Okay. Yeah. So, as Dieter indicated, there are the actual signaling packets, and there's the radio subsystem layer, which contains messages for radio link layer, dedicated channel, common channel, and transceiver management. What we're going to focus on is the radio link layer, because the radio link layer in turn contains the messages for call control. So that's the actual Q931 derivative that does the call setup, call proceeding, alerting, and so on, indications like in ISDN. There's mobility management, which is for actually like roaming, knowing where a mobile handset is, registration, handover, and so on. This is radio resource, which is, as the name indicates, about radio resource management, and short message is a separate layer. Those are mostly specified in GSM specification 04.08. I think that's about 1,000 pages, so it's not all that much in GSM terms. The system that we have right here is a Siemens BS11 micro BTS, and that Dieter is going to cover a couple of slides about that one.
Okay. Harald already told you that this is a Siemens based transceiver station. It is originally manufactured by an Italian company. It is manufactured for Siemens, It supports, basically it supports the old GSM 2G network. This means voice calls. It might support data calls in a very, in some previous specification before GPRS, but we have not yet tried that out. So it might be possible, but till now we are 100% sure that it works for voice calls, but we don't know anything if we can support data calls in the future. The interesting thing for the base station transceiver is that you can set up the power which it uses on the output. There are 4 stages between 13 milliwatt and 2 watt, and you can choose which stage it uses. So even if you should not try it at home, if you try it, turn it down to 30 milliwatt, then probably you don't disturb too many people. You should not use the 2 watt because this is the power similar to your phone, so you will have a really huge range. The antenna is a directional antenna, so you usually have a 100, let's say roughly 180-degree transmission direction. But anyway, I would suggest if you try it, even if Harald says, okay, don't try it, then turn it down to 13 milliwatts.
Or even add additional attenuators in the RF path.
Of course, this is the recommended way, but if you don't want to spend the money on the attenuators, you know what to do.
Yeah, we actually, somebody from the team verified the output that actually is only 30 milliwatts. So.
Yeah, we can trust this configuration if it's really set to it. Yes, as it's measured, we have measured it. It's really only 13 milliwatts. Okay, the interface. In our case, to our software, the base station controller, this is going over an ISDN interface, and the base station transceiver has 2 ISDN interfaces. We use one to connect it to our base station controller, and currently the second one is not used, but it could be used to daisy chain several base stations. We have a lot of time slots on our ISDN channel 31, and we only need if we support all the capabilities of the space station, we would only need 3 or 4 time slots at all. So we have several spare ones which we could use for other base stations which are daisy chained over the second ISDN E1 interface. When we started with this project, we got some documentation, but this documentation is under NDA. But this documentation, actually, it's not details about how the protocol works, or it's not even details about the hardware looks. Basically, it's something like how to mount the station on the outside, how to make sure that it's waterproofed, how the intrusion detection works, so if someone tries to mount it off the wall, what happens, and such things. So it's not really documentation which is very useful if you want to develop software for this device. So as we said, it's under NDA, we cannot give it, we cannot forward it or put it in the public, but anyway, it's not that interesting to have it because really it's about mounting and such things. And you find most of the specification of how this device works, you will find in the GSM specs actually. When we started with exploring the capabilities of the space station, we were not really aware that all the specification of the protocol is available. The reason is that the ABIS protocol for configuring the base station. Configuring means in this case setting it up. Telling the base station what frequency it should use, what time slot it should use, and such things. This is not the messages you need to communicate with the mobile, but you needed to set it up that it initially starts up. We thought that this messages and this protocol is really specific to the manufacturer of the base station. This was the case, I think, for base stations built before, probably the late 90s. But then GSM introduced a specification which clearly defines how this setup procedure works. And our base station, luckily, really conforms, let's say, 99% to this specification. So we can look it up and see what we can do with it. And this is also a big advantage because in the NDA docs there was also no information about how this protocol should work. Basically, an operator who buys such a base station does not need this information. He, of course, buys the software from the same supplier for his base station controller, and so he does not care what's going on the line. This base station, additionally to this ABIS interface, which is going over the ISDN line, it also has a serial port. The serial port is connected to a program which is also under NDA, which is called LMT for Local Maintenance Terminal. The software basically is used for the service people in the field. They can plug it into the base station, they can check certain settings and adjust some of the settings. But most things of those settings can also be sent over the ABIS interface and is available in the specification. So this program is not that very useful. If you don't have it, it does not care that much. There are a few commands which are interesting. For example, the commands to set up the output power of the space station, and we will provide this information of how to send a few bytes and get back a response from the base station in the wiki. So if someone wants to use the few important commands, all of them will be provided, of course.
Okay, we have to speed up a bit, so let's just go quickly through the couple of pictures.
Okay, here is one of the pictures of the interiors. It's really tricky to get inside. We will provide the information of how to get inside because this is a unit which is used for outdoor usage, and it's really very well closed. So, but when you open it, you can basically see the power supplies, two power supplies, because we have two separate transmitters in this unit. One transmitter can have 8 time slots, and we have 2 of them. There are the filters and the low noise block, which is connected to the antenna. There is the baseband part. The baseband part is basically processing the digital streams which were already demodulated, or which process the data which have to be demodulated, modulated and later transmitted by the system. We have several huge parts in the left, which are the transmitter and receiver. You only see this large block, but actually they are stacked. There are 4 boards stacked over, and they contain those information. You can see it here on the next picture. That we have several levels. The layers are stacked, and the interesting thing, this is really handmade work. There are a lot of metal is inside. Metal is basically, in this case, used for thermal transmission of all the heat which is produced inside. This base station was manufactured about 10 years ago, and we don't have one single microcontroller which can do a lot of things. No, we have several. We have about 6 or 7 microcontrollers, 8 DSPs, and all of them produce a lot of heat. So therefore, there's lots of metal inside.
Yeah, so actually this talk is about how to operate your own heating.
Yeah, and if, as Harald already said, if you touch the base station after it is running for about half an hour or so, I would say in this position where thermal transmission to the air is not that good, we have about 40 degrees on the top. And here in this picture you can see the 2 layers for each of the transceivers in the base station, and each of this layer is divided in a transmitter, in a transceiver, and in a transmitter and in a receiver, and really large PCBs inside. And as I said, every chip is connected to the upper layer with some thermal paste, which dissipates the heat to the upper layer and then finally to the outside case. This is the interface connection. Here we find on the top, we find the connectors to the RF antennas. We have, as I said, we have 2 transceivers, so 4 connectors, 2 antennas for transmitting, 2 antennas for receiving. On the lower part, we have the We have the E1 interface. Those are the coax-like looking connectors. There are two pins inside. It's not the standard BNC connector you might know from old Ethernet, but they contain two. And below below is the power connector, and in the middle you have the connectors to the RS232, and there's also a switch to turn it on.
Yeah, sorry. That's
the important one.
The switch is here, yeah.
The switch is here. If you really think you are disturbing someone, turn it off.
Yeah.
This works all the time.
Yeah, yeah. It's an actual like primary line power switch. It's not one of these soft standby kind of things. So anyway. So how did the first steps happen? Well, basically I bought the first, well, literally this unit, which is here, in 2006, if not earlier. I started to read some specs, started to build the cables for E1 and power. The power cable was particularly tricky, I can tell you, because the power plug has 4 pins, and according to the documentation, 2 of them are connected to phase. One is ground, the other one is earth. It's like, okay, 2 times phase, ground, and earth. So you connect the phase, like the actual line, to the 2 phase. No, it doesn't work like that. Anyway, so all that has been resolved. I bought an HFC E1 card, which is a primary ISDN primary interface card that's frequently used with Asterisk, bigger Asterisk installations, for example. It's supported by MISDN, which I even then intended to use as a base for the software. I also managed to find an ABIS analyzer on eBay. It's a handheld device meant for service people of GSM networks, which you can tap onto the ABIS interface, and then you can see what's going on. I also managed to get in touch with some other people who also happened to end up with one of these devices or more, luckily found somebody who has not only BS11 but multiple base stations, even different ones, and a base station controller who could send me traces of the ABIS protocol from an actual live test network. So using those traces, it gets much easier to do anything, but then unfortunately around that time I got involved with OpenMoko, so all that was halted or stalled, and yeah, well, Dieter came around in this year.
Okay, I was reading in Harald's blogs that he has the space station controller and the space station, and I really thought, oh, this is great. I always wanted a base station too, and I thought how to get one. Taking one of those bigger base stations apart, which you find sometimes near the road, was not an option for me. So when I heard that Harald bought one, I was looking on eBay, and luckily, it's really at the same time when I was looking, there was one offered, and I bought it. I also bought the E1 PCI card, the same one which Harald uses from Cologne chips, and I'm coming from the Windows side. I'm not coming from the Linux side, so I thought I want to try it out on Windows. I got a reference driver from Cologne chips, but this reference driver is actually a really simple demonstration of how this chip can be used, and it was intended for MS-DOS only. It does not use interrupts, it's just polling. Okay, I thought maybe a good idea to find out how this chip works and to see what is really going on the lines. Yeah, and I started with a very simple program, and step for step found out how to communicate with this base station. Of course, very useful were those traces which we received from another person who already traced the base station with a simulator and with an analyzer. He does not wrote his own software, but he had a simulator which could implement a base station controller, and it is mainly intended for testing these base stations. And the traces from this device were very helpful to get it up and running. This is just a simple screenshot of this initial program. Also, it is really polling and not doing anything fancy. In the end, it was possible to set up the base station, to let the phone ring, even to save some of the voice channels, saving in this case, not really hearing it real time, but saving the file, and later on taking a few command line tools and finally get out what I've talked into the phone a few seconds before. So this was the start from my side.
Yeah, so that sort of triggered me to revitalize my interest, also given the fact that I meanwhile had departed OpenMoko and had a little bit more time at my hands again. So actually this month, well, I wanted to start in September when I heard about the first results that Dieter was making. And then it took me some more time until I finally could allocate a time slice. Started to work with MISDN on the Linux side, and MISDN has a kernel-side implementation for the NT mode of the Q921, which is the layer 2 management protocol, the TEI assignment. Had to patch it a little bit to support multiple SAPIs and fixed TIE allocations, but that's like a 10-line kind of hackish patch, so a very, very easy thing. Then I had to figure out how the new sockets-based MISDN APIs work, and then I came up with some event-driven architecture for the actual program, single select loop, no threads, nothing fancy. So the stuff that we've been working on here at the 25C3 in the last 3 days, actually, we added a lot of stuff to that. A number of my friends from OpenMoko and OpenEasyX started to add stuff. So now we have a libdbi, an SQLite database backend for the, well, HLR in quotes. It's not really an HLR, but it's basically a table which contains all the information that we're interested in so far or right now, like the TMSI allocations, the IMEI, IMSI, and so on. We got the paging to work. We have support for configurable network ID, so we can say we are some other network. We have tried to say we are Iridium, but unfortunately the names of Iridium are not in the standard GSM phones. It would have been so fun if people look at their regular phone like, oh, Iridium, where am I? But doesn't work that way. So lots of debugging and stabilization, and the interesting fact was we have more than 1,000 test users. There's lots of voluntary test users here, which is a big surprise to me, considering the fact that like especially 963 of those 1,000 test users are German German subscribers, where their home networks are here. So why would your phone ever not register to your home network, but to some foreign network? That's really strange. But despite that fact, people kept trying, and actually was a stress test for the entire software architecture. Would never have been able to debug that kind of load while sitting at home. And one of the first things one of the first things that I did was to implement the IMSI and IMEI skimming, which is obviously fun to do, and I'll get back to that right now, actually. So what this is actually very simple. So when your phone wants to register to a network, so first of all, your phone decides that it wants to register to the base station, which is completely weird considering that it's not using an operator ID that you have. Like you have your subscription with T-Mobile or whatever, and we use a network ID that's 0101. It's a testing ID. It's not your home network. So we're not claiming that we're T-Mobile. This is not a kind of impersonation attack of any sort. Your phone decides, oh, we should register to this network. And then we basically, it sends a location update request, and we tell it, well, we don't know you. Please tell us your IMCI and IMEI. And the phone happily responds because, as I said, the network has the intelligence. The phone is just, a stupid device, and it just responds to whatever the network asks it for. And since the network is not authenticated, you get that information. So that response gets back. We put that in the database, and then we tell it, oh, go away. We don't want you. So they happily go off, log into their regular network, and we have their IMEI and IMSI. last night, actually, I didn't sleep, and I wrote a Perl script. Well, the Perl script didn't take me all night, but the last thing I did before writing the presentation was to write a Perl script to do some statistical analysis on the data we gathered. And I can maybe we have a minute later on, but basically, I have statistics from which country people are coming, to what percentage, and these kind of things. Another thing that you could do, which isn't implemented yet, is like statistics, what kind of mobile phone is the most sort of well-known one. Interestingly, there was one IMEI which was clearly spoofed. So there's at least one person here who had... There's one person here who sent an IMEA of 000123445. Okay, now mobile originated call is actually fairly simple because once you say location update accept and the phone is basically in your network, then the phone can just dial any number. You make your outgoing call, you send a channel request, the network responds, channel acknowledge, and you deal with the signaling layer and get the connect. Unfortunately, in this, what I call OpenBTS software, we do not have the voice data processing implemented yet. I was hoping to get it done before this talk, but unfortunately we didn't. It's probably 1 or 2 days away. The mobile originated SMS is also like from the lower level signaling fairly simple. The actual hard parts are probably when you get into the parsing of the PDU and so on. But luckily, the person who just did that for a free smartphone on the handset side, well, was now happy to do the network side as well. So we have that implementation there. So you can send SMSs and it will be displayed on the Linux console. And actually, interestingly, last night, somebody sent an SMS over our network. Like, not one of us testing that, but somebody like, oh, I found a nice spot next to the OpenWRT in the hack center. It's like, okay, thanks for telling us. So we quickly switched off accepting other people into the network again because, yeah, it starts to get nasty. So then we had the Egypt simulation. Apparently, GPS is illegal in mobile phones in Egypt. I tried to Google and found a number of pointers. Apparently, that's the case. And mobile phones that are at least officially sold by operators in Egypt have the Egypt detection feature. So once they see a base station that has a country code of Egypt, they switch off the GPS. You don't even have to register to that base station. Just only if they see it somewhere in the vicinity, they say, oh, you know, we're now in Egypt, we have to switch off GPS. Which is interesting. Not all phones do that, but we've had some Nokia phones, and I think with the iPhone it was not quite clear, but apparently it also seemed that way. And yeah, so now basically you have something like a GPS jammer, not even doing anything related to GPS. So there's some other GSM-related free and open source software that I want to talk about before we get into the demonstration, which is OpenBTS actually, which is almost, how can I say, almost a good combination, because we are using an industry manufactured base transceiver station, and OpenBTS is about writing that as software-defined radio based on GNU Radio and USRP. And they've just had their 1.0 release, I think 1 or 2 months back, and it's sort of, they implement, the BTS is sort of a misnomer. They implement the BTS, they implement everything, and then attach that to I think SIP, voice over IP calls. And obviously there is quite a bit of overlap, and we are, I think right now somebody should land in Berlin 2 days delayed because of weather implications, and we will talk about how we can align our work in order to benefit from each other. In any case, the base station controller part is more something that I feel familiar with because it's network protocols after all, and that's sort of my home. Yeah, there's some other links that you might want to check out. We will put the slides online, obviously, at the Congress website, so you can check out all these links. A couple of thanks in the end to various people, and we're going to switch to a demonstration now in, well, about a second, where hopefully I will see some cameras rotating away from us now.